Hi everyone. Today I will talk about k-mers. This is a term that you often hear in the context of sequencing data analysis. So k-mers are short substrings of the sequence read which are of fixed length k. And because of their simplicity and scalability, you will see methods based on k-mers used in a wide variety of bioinformatics applications. And I've just listed a few of them here. So it goes without saying that it is very important to store a set of k-mers in a space-efficient way. And there are some lossless approaches to do so. But today I will mainly talk about our approach, which is based on Unitix. So we start with a set of k-mers S. Now, a set of k-mers is closely related to the notion of a De Bruijn graph because in a De Bruijn graph, every node is a k-mer from the set and there is an edge from k-mer x to k-mer y when the suffix of length k-1 of x is equal to the prefix of length k-1 of y. Now, let's look at a k-mer set S, which is a spectrum of a single genome with no repeats longer than k-2. That simply means we have a graph that consists of a single linear path like this. So a naive way to represent this set is just write down each of the k-mers one by one, and that will require n times k nucleotides. So here n is the total number of k-mers. And the number of nucleotides in a representation is what we are going to call weight from now on. Okay, so to find a space-efficient representation, all we have to do is find a representation with low weight. Okay, so it has been shown that any k-mer set representation will have at least n nucleotides in them. And for this particular example, I can show you that there exists representation with weight n plus k-1. How do we make that? So for that, we take the path that goes through each of the vertices and we try to spell along the path. So for the first k-mer in the path, we write down all of the nucleotides, and for the remaining ones, we only write down the last letter of the k-mer. So thus we get a spelling of the path CATTG. So this is a space-efficient representation of this set, k-mer set. Okay, and the interesting thing about this representation is that every k-mer from this set appears as a substring in this red representation, and also any substring of length k from this red representation is going to be in the original k-mer set. Okay, so but that is a very simple example, and in practice you often see a more complicated example like this where the graph has many branches and it's not entirely linear. However, the De Bruijn graph will still exhibit linear structure in between the repeats, and I've marked those linear paths in this graph with red rectangles. And this kind of linear paths have a special name for them in literature. They are called unitics. To formally define unitic, unitic is the maximal path where the internal nodes are one in and one out. The first node in the path can have multiple ins, but one out at most. The last node in the path can have multiple outs, but one in at most. So you can see that following the same process as before, we can spell out each of this path to have a small weight representation of the k-mer set. And when we replace those paths with a single vertex and get a graph like this, we call it a compacted De Bruijn graph. Here, the weight is determined by this formula, n plus number of unitics times k-1. And like before, these unitic strings have the special property that they are a decomposition of the k-mer set. That means if there's a k-mer in this set, say for example CAT, it's also going to appear as a substring of one of the unitic strings here. and vice versa. So what is so special about unit tests that make them so useful? It is this characteristic that they contain the same k-mers as S and only contain them once. Let's call a set of strings that honors this property a spectrum preserving string set. Okay, so a little side note here. So we've generalized the concept of unitics to spectrum preserving string set, but this was also simultaneously and independently introduced by Brinda et al. Under the name simplitics. So simplitics and SPSS basically means the same thing. Anyway, so for this graph, we see there are two possible SPSS representation. One is the set of k-mers based representation, which has a higher weight, 33. And on the right, I have this unitics set based representation with a smaller weight, 21. Now, unitics were not originally introduced as a means to find low weight representation or space efficient representation. Rather, it is a concept borrowed from the world of genome assembly. So maybe we can do better than unitics in terms of representation. So that's why we ask ourselves, are there SPSS representations that have smaller weight than unitics? And can they be computed efficiently? And if they can be computed, what is the lowest weight achievable by such a representation? Can they seamlessly replace unitics in downstream applications and improve space? Okay, so the good news is by the end of the talk, we are going to have the answers to the questions. So let's get started with answering those questions. So the first thing to observe is that the weight of an SPSS is number of k-mers plus the number of string in the SPSS set times k minus 1. This means in order to find a low weight representation, we have to reduce the number of strings in the set. For that, we notice that there is an equivalence between an SPSS with I strings and a vertex disjoint path cover with I paths. So I'll explain that with the figure here. So here, I've marked in red the paths in this graph. And there are 5 paths here, and each of these 5 paths constitute a vertex disjoint path cover where every vertex is in exactly one path and no path visits a vertex more than once. And also notice that for each of these paths, there is a string here, a spelled out string here in red. So that tells us that to reduce the weight of an SPSS, we have to reduce the number of paths in the vertex disjoint path cover. So what we do is we propose a heuristic to find that. Okay, so our heuristic is called unitic stitch, or in short UST, because we start with a set of unitics computed by the tool become2, and we know that when we have those unitics as a vertex in the graph, that graph is called the compacted de Bruijn graph. And in that compacted de Bruijn graph, what we do is we start at an arbitrary vertex, and we try to extend the path of that arbitrary vertex as long as we can. And we repeat this process until all the vertices are covered. So in this example, let's say we first start with AAC, and then we try to extend it, and there are 2 ways to extend it. Let's say we go with ACGG, and then we extend it with GGA, and now that we've hit a dead end, we have to output the path here and output its corresponding spelling, which I've shown here in red. Okay, and also for the remaining 2 vertices, we do the same, and we output the path and its corresponding spelling of the path, ACT, GGT. So our algorithm finds 2 paths in this vertex disjoint path cover, and equivalently it finds 2 strings. However, our algorithm is not guaranteed to find the optimal number of paths, or in other words, the lowest weight every time, because it's a greedy algorithm. It might end up having 3 paths instead of 2. So then how do we say how good our algorithm is? We have to find a lower bound to compare it against. So how do we find a lower bound? We need to lower bound the number of paths in the path cover. For that, notice that every path has a start point. So if we can count the number of nodes that must be start points, we automatically get a lower bound of the number of paths. Okay, I'll explain that with an example here. So in this example, I have 2 red vertices, which are source vertices. That means they have no incoming edges to them. So they must be start points in the path, in whatever path cover they belong to. Okay, now let's try to tighten the lower bound. So here, all of these 3 blue vertices, they have a single predecessor x. Now, when we're trying to extend the path of x, it can be predecessor in its predecessor of only one of the, at most one of the blue vertices. So for the remaining 2 blue vertices, they have no choice but to be the start points in their path. Okay? Okay, so that tells us that there are at least 4 start points, 2 red and 2 blue start points in this graph, and that's why there are at least 4 paths in our graph. So now that we've established a lower bound on the number of paths, we can get a lower bound on the number of weight. So let's get to results and see how our algorithm UST and the another SPSS representation Unitix perform against that lower bound. Okay, so for our experiments, what we did was we downloaded 5 different publicly available datasets and we computed k-mers from them. We filtered out the k-mers that appear only once in the dataset, and thus we ended up with having 100 to 400 million k-mers. So we see that in the result, UST is better than Unitix by 10 to 32%. Now, what about the lower bound? When we compare it against the lower bound, we see that there is only a 2 to 3% gap between UST and the lower bound. So this is interesting because it tells you that the greedy algorithm performs reasonably well in practice. So even if you have a non-greedy perfect algorithm to find the minimum vertex disjoint path cover, it's not going to improve results that much. Okay, now let's consider some applications of UST. So UST did give us a small weight representation of the k-mer set here. But what we can do is we can compress it even further with a DNA compressor called mfcompress to get a file that's in size 3 to 4 bits per k-mer stored in disk. So this uses a lot less space than BOSS and Unitix. Okay, and you can also store counts along with those strings. So when you do that and compress everything together, you end up having a file with 4 to 6 bits per k-mer. So in both cases, we see that the UST representation performs better than its competitive approaches. Okay. The second application that we consider is UST-FM, which is a membership data structure. A membership data structure supports fast k-mer query without any decompression. So it's like you have a k-mer, you ask whether it is present in the database or not, and this data structure will answer that on the fly. Okay, so for UST-FM, we built this data structure by taking those strings and building an FM index on top of them. And with this membership data structure, we've shown that it improves the size of index by 25 to 44% against BOSS and 10 to 32% against Unitix. Okay, so we are able to answer the questions that we presented earlier. So we've shown that there are spaces representations that have a smaller weight than Unix, because UST is better than Unix by 10 to 30%. And they can be computed efficiently because we have introduced a simple polynomial time greedy algorithm. And in order to answer what is the lowest weight achievable by such a representation, we provided a lower bound on the size of the optimal SPSS and showed that our algorithm is nearly optimal with respect to that lower bound. And we've also shown that UST can seamlessly replace Unix in two downstream applications, one UST compress and two UST FM, which is a membership data structure. Okay, so we're not free from limitations. We like the first step where we have to build a compacted De Bruijn graph using BCOM2. It takes up a lot of time and memory. And also the compression method that we've discussed, UST compress, it's not necessarily the best available, best possible thing, because you can achieve more compression by going beyond SPSS. So with that, I'd like to thank my funding sources and Ryan Cheeky for his help with BCOM2 and his feedbacks. And if you're interested in the software, go check it out in our GitHub page. It's free to download. And with that, I'd like to end my talk. And thank you everyone for listening.